Well, welcome to our first Winfield United Agronomy training for this year. We're really excited to start having these basically every week. We're going to have one of these going through a bunch of different topics. Darren and I were debating on whether we should sit down and do one whole class on plant nutrition and do it for 3-4 hours on Zoom. But guys, it really we kind of settled on this hourly thing every week, mainly because we thought it was a lot of information to do over a Zoom meeting. We also did think about having this in person. The main reason we didn't is because of the amount of traveling that you'd have to do a lot of you would have to do to get there. It just didn't seem like there was a good spot where a majority of you could actually get to the training. And so we did decide to do this as a virtual training. Now, even though it's virtual, Darren and I have quite a few different demonstrations set up. We will be doing all of our live demonstrations. So it will be entertaining, and we'll try to keep it as lively as we possibly can going through each one of these. Okay, we're going to start with crop nutrition and discussing all of the different various aspects of crop nutrition. So today we're going to start with the introduction to crop nutrition, soil productivity, and soil pH. And then we're going to continue over the next 3 weeks after this to discuss all the various nutrients. Okay, then after we get done with that in October, the very end of October, we're going to switch over to crop protection. And we're going to do about five weeks on crop protection. And then finally, the last 3 weeks, which are in December, we are going to take a break there for the Thanksgiving holiday there. The last 3 weeks in December, we're going to finish up talking about sprayers, talking about adjuvants, mixing order, clean out, all of that information. Okay, so that's the plan. That's what we're going to be covering all throughout these weekly calls. And I'd encourage you to make as many of them as you possibly can. For those of you who haven't been through this training, it's a really good, hopefully easy to understand process here. For those of you who have, I'm hoping that you'll pick up on some new things. I got some new demonstrations, actually a brand new one today that I'm going to try out live that I've never tried before. So it'll either go really, really well, which will make it very interesting for all of you, or it'll go really, really poorly, which will make it still fairly interesting for you guys. So we will see what ends up coming of that. So to start with, though, I do want to talk about a little bit of an overview of crop nutrition. Okay, and to do that, I know a lot of you have seen this before, but hopefully you guys can see me now on the screen. Darren, can you confirm that?
Yeah, we can see you.
All right, perfect.
Looks good.
Perfect. So this is my rendition of a stave and barrel. A lot of you guys have heard of the stave and barrel approach to plant nutrition, right? The most limiting factor in a plant nutrition system is what's going to limit your overall yield potential. Okay, so in this case, zinc is our most limiting factor, right? That's where we're losing all of this yield potential. And no matter what we start looking at for all of these other nutrients, I could put more, for example, potassium out in that field. I am not going to increase the yield though, because zinc is my most limiting factor. Okay, now I can go out there and I can fix zinc. If I would have designed this box a little better, I probably wouldn't have made the pegs the same size as the corn that goes into it, but we'll shove some zinc. Oh, it's backwards, that's why. Shove some zinc in there, block that hole. Okay, now we have more yield potential, right? But here's the frustrating thing when it comes to plant nutrition. Okay, we're trying to fill as many of these gaps as we possibly can. But just because we fill one gap doesn't mean that there's another one that might also be limited. Okay, so you have to think of plant nutrition as a holistic approach, right? We have to correct as many of these nutrients problems as we can, and it's not usually a one-year process. Okay, I really encourage you, and not all farmers are necessarily going to be up to this challenge, but I really encourage you to take those more progressive farmers, utilize their soil tests as the basis for their crop nutrition program. And Darren's going to spend a little bit of time on soil testing and some of that stuff. And as we go through, we'll talk about soil testing. That needs to be the base for your plant nutrition program. I also encourage you, though, to look at some of the deficiencies in season as well. Okay, we can really efficiently correct things like phosphorus, things like zinc, or things like potassium, things like nitrogen by putting more in the soil. Okay, but sometimes in season, we end up running out of things like zinc. Okay, and that's where a tissue sample can help you identify your gaps in your nutrition program. So continue to fill this, until eventually, now sulfur is our most efficient nutrient. Okay, and again, it's a process. It's about building these nutrition programs over time. Unfortunately, guys, there's not one single nutrient that you can add to accomplish all of your needs. Also, it's not like you're ever really done. So we take a look at some of our tissue samples, right? One of the best things that can happen with a tissue sample is you go in, you find that there's a deficiency, you make a change in that farmer's program, and the next year you come back and find, oh my gosh, there's a different nutrient that's deficient. Because what's that saying is that you fixed the one nutrient that was limiting your yield potential, and now it's a different nutrient. Okay, so it's a continual process. You have to continually build that yield. You have to continually move that mark up so that you can continue to increase your overall yield potential. Now it's interesting because some farmers, as they're building this program and as they're finding success with increasing their overall nutrition program, one of the things that I have commonly happen is, well, okay, is that zinc really doing something for me? Here's the thing, guys. A lot of you guys have heard of some of the work that Fred Belo's done down in Illinois, right? Basically, what his data showed is that when you removed one thing from the system, you actually oftentimes lost more yield than if you were to take that exact same input and put it into a lower yielding system. Okay, and you can see that really well here, right? We built this yield really nicely up to the top of this box. We've increased our overall yield potential. However, let's say the farmer decides, well, I'm spending a lot of money on zinc. I'm going to remove that zinc. I lose a lot more yield potential by taking that zinc out of that system than I did even adding it in at the beginning. So as you build this yield, help that farmer remember the reason that their yields are increasing. Help them remember that each one of these systems is interacting. Each one of these different nutrients have to be there to basically allow those other nutrients to work. So as we go through and talk about all these various systems and all these, today we're going to talk about soils and pH, as we're talking about potassium, nitrogen, sulfur, zinc, every single one of them is important to the system. Okay. Now it's also important to remember, guys, that if you get all of your nutrition right, but you don't take care of things like weeds, insects, diseases, you don't plant the crop right, you don't do all of those things, it's pretty dang easy lose your yield potential out of the backside of this box as well. Okay, so we need to do the best job that we can to manage as many of these various yield robbing factors as we can. Okay, now as we start talking about some of the key things around plant nutrition, I'm just going to switch back here. We got some of the key things that we need to talk about with soil nutrition. There's 17 essential nutrients that we have to apply, and that the nutrient or that the plant has to have to complete its cycle. Okay, so these 17 essential nutrients are going to be critical to our overall success when it comes to plant nutrition. Now, not all of these do we apply every year. In fact, some of these we have plenty of in the soil. And so then we very rarely have to, if ever, apply them. So things like chlorine or copper sometimes, molybdenum is rarely deficient, nickel is rarely deficient, calcium, magnesium, rarely deficient. And so some of those we don't necessarily worry about, but each one of these is very important to make sure that we're getting our fullest yield potential and to have that plant complete its overall life cycle. Darren, I'll turn it over to you.
All right. Okay, let me share my screen. Okay, can you see that okay?
Yep.
All right, and I'll share my video here while I'm presenting. Okay, good morning, everybody. Appreciate you jumping on the call here. As far as the soils portion for today here, Tyler mentioned at the beginning, some of you have been through this or different versions of this. Some of this might be fairly basic, but it's always a good review, particularly those of you that might be studying for the CCA exam. This is probably a good review of some of those basic soils topics. But to kind of move through here, so first off, what is soil? And like I said, this starts very basic, and then we'll build it from there. So just as a refresher, so it's about 50% minerals and organic matter, solid material, and then the other 50% is your pore space that's made up of water and air. Okay, that mineral fraction, we'll talk a little bit more in depth on the sand, silt, and clay here in a minute, but that makes up the mineral fraction of the soils. And then the organic fraction, the organic matter, that's your decomposing plants and animal residues, your microorganisms that may be out there in the soil as well. One thing to keep in mind, though, as far as soil, it is a source of nutrients, and as far as crop productivity, crop production, it does provide a lot of the nutrients that we need out there. And there's this, these interactions that we have to deal with as far as the nutrients becoming available, being mineralized, and becoming available for crop production. And then the soils, they can also tie those nutrients up, and so they're unavailable for crop production. And so that's some different things we need to deal with in managing those soils. So that's a little bit about what the soil is. Now, what does the soil do? Okay, a number of different things here. One is regulating water. They help to control the movement of rain, snow, and irrigation. I'm sure when we get to the nitrogen portion, we'll talk a little bit more in depth as far as how quickly the nitrate can leach down through that soil profile. But based on if we're dealing with a heavier textured soil, heavy clays versus a sandy soil, water movement's gonna differ pretty drastically between those different soil textures. Second thing is sustaining plant and animal growth. So they impact the diversity and production of living things. Third is filtering and buffering potential pollutants. And then some of the other key ones down here, cycling of nutrients, like we said. So organic matter, it is a source of a lot of different nutrients. And then soils in general provide, you can see a list there, carbon, nitrogen, potassium, phosphorus, zinc, sulfur, a lot of other different nutrients are either stored or transformed in that soil profile. And then the final one is around soil structure, so physical stability and support for the plants to grow in. Okay, so the plants have good standability out there. Okay, so that's a little bit about what soil does. Going a little bit more in depth here on soil texture. We've mentioned before sand, silt, and clay. So your clays are the smallest there, 0.002 millimeters. And then going up from there, you'll see the silts are a little bit bigger. And then sands are quite a bit bigger than that, all the way up to 2 millimeters. And then anything over 2 millimeters, we'd say that that's gravel. So it gets pretty big after that. One thing that's kind of interesting, though, is over on the right there, it says clay has 1,000 times more surface area than an equal weight of sand. Okay, and so you might look at those, the size, the relative size of those particles and think, you know, how could that possibly be? Sand is so much bigger than clay, but because of how small those particles are for clay, there's a lot of surface area, and how the clay lattice, the structure is in the soil, it creates a lot of surface area. And we'll get into CEC here in a little bit, and so clays have a lot higher CEC, or cation exchange capacity, than sands. And part of that has to do with the surface area and the charge along that surface area. As far as soil texture, this kind of lays it out here. A lot of times we do talk about you know, fine, medium, and coarse soils, just kind of general groupings with those. And so with that, you'll see the fine, that's in the turquoise area at the top. So these are more of our soils that have a higher clay content. Our medium textured soils are there in pink. These are our loams that have a good mixture of sand, silt, and clays. And then the bottom left there, these are our coarse textured soils in yellow that have a higher concentration of sand. Okay, but knowing the different percentages, we can kind of figure out, you know, what is our soil texture. So for example, if we were to say we have a 20% clay and a 20% sand and a 60% silt soil. Okay, so we basically find the meeting place of all those. So we've got our 20% clay, so that's down here. We've got our 20% sand, that gets us to here, and then 60% is what's left, so 60% silt, and so we'd be dealing with a silt loam soil. Okay, so that's one way to use that textural triangle, but we don't always, you know the exact percentages of sand, silt, and clay. Most of the time we don't, and there are some quick and dirty ways to do it out in the field to try to get an idea of the particular soil texture that we're dealing with. And you can see it listed here, you know, all the way from coarse soils down to fine. You know, obviously with coarse textured soils, you're probably all taking a handful of sand that has that gritty feel to it. And then by the time we're dealing with these soils that have a very high concentration of clay, we can form a good ribbon. And so that's what this is saying here. You know, you take a handful of that soil, and then you try to push out a ribbon. And if it forms a ribbon that's 2 inches or longer, we'd say that would fall under this sandy clay, silty clay, or a clay soil. Okay, so more of the fine textured soils. So that's kind of a rough way to identify them out in the field, what kind of soil texture you're dealing with. And I guess one thing I will mention, we will send this information out after the call. We'll forward it out to the Winfield United team, and then they can forward it out to different folks as well. So you should be able to get a copy of this afterwards as well. Okay, so another principle that comes into play as far as soils relating to crop production is the water holding capacity based on our soil texture. And so there's some different terms that we often hear related to water holding capacity. One would be, so saturated soils. Saturated soils is anything above this line here of field capacity. So with our saturated soils, that's where our water is draining by gravity out of the soil profile, okay? And once the water stops draining by gravity and the soil is still holding water, we'd say we are at field capacity, or the upper limit of what that soil can hold in its pore spaces, okay? And then below that, as the soils dry out, this is our available water, okay, for the crop. And then eventually, like this last year, where it was extremely dry and we didn't get a whole lot of precipitation in a lot of parts of the state, eventually we do hit this permanent wilting point, where, you know, once our soil water goes below that, there still is a tiny bit of water in that soil, but it is so tightly held to the soil particles that the plant can extract it from the soil. And so those plants are permanently damaged. Okay, so that's the permanent wilting point. Is even after that, if we caught a rain, the plants have been stressed enough that they can't recover from that water stress. But in between there, in between field capacity, permanent wilting point, we have plant available water for uptake. And you can see this band is wider in the middle for our loams compared to the sands or the clays. Okay, and so the clays can hold the most water, but as far as being able to, it's tightly held in that pore space compared to the sands. They don't hold nearly as much water. They have macro pores, and so the water drains more freely. So they're not able to store nearly as much water compared to some of these loamy soils. Okay. So water holding capacity, some of those general terms. Field capacity, permanent wilting point. Those are some of the common things that we run into. As far as nutrients in the soil, you know, they're located in many different areas of the soil. Some are not available, some are slowly available, some are readily available. And so we'll just kind of walk through that here a little bit. So some of them are fixed or very slowly available in between those clay layers. And so without getting in depth too much into soil science here, with this one here, so the clay structure in the soil, it's made up of different layers. And so this would be an example of a 2-to-1 clay. So sometimes you hear about 1-to-1 clays, 2-to-1 clays, shrink and swell clays, things like that. So this would be an example of a 2-to-1. So it's got 2 silicone layers to 1 aluminum. Okay, so that would be a 2-to-1 clay. And then in between here, we have different nutrients that can get trapped in between that clay lattice out in the soil. Okay, so some of these you'll see listed there, these different cations get trapped. And so you know, based on our soil moisture, some of them become available for crop uptake, and some of them are fixed in between that clay lattice. Okay. Some of the nutrients that we have out in the soil are bound along the edge of the soil particles. Okay, and so there's these different the clays have charge to them. And so that negative charge, it'll attract the positively charged cations, and it'll hold those, and this gets into cation exchange. Okay, and so with this here, you'll see the positively charged cations are tied up or held on the edge of those clay particles. Okay, some nutrients are dissolved in water and they're readily available. As the roots are out here kind of sucking up this water, with it they can bring in different nutrients, and you'll see some of them that are highly mobile are nitrates, are NO3 minus. are sulfates. They're negatively charged, and so those aren't held on the soil. That negative charge on the soil actually repels the nitrate and the sulfate, and so those move freely in that soil solution and can easily be taken up by the crop. On the flip side of that, they can easily be leached with additional rainfall. Okay, and then the final portion here is the nutrients that are in organic matter, and they need to go through this mineralization process to become available. Okay, and so that would be very slowly available nutrients. Okay, a little bit more on organic matter. You know, there's different parts of organic matter. One huge topic that comes up is soil carbon, and that's tied in here as well with organic matter. As far as, you know, how can we measure soil carbon and changes over time to soil carbon based on our management practices? That's a topic that we're going to hear more and more about as we move forward. But organic matter in general, it's got these different parts, some that are, you know, the decomposing or active fractions, some that are the stable humus portion, and then, you know, fresh residues and living organisms. Okay, but we've got these different fractions. Organic matter, similar to clay, it has negative charges around it, and so it does provide nutrient exchange, so cation exchange capacity as well. And then because of that, it's a source of these essential plant nutrients as well. So I'd mentioned before, you know, with organic matter, it is a source of nutrients, but they do have to go through mineralization. And then based on the material that we're adding back to the soil, we're in the fall now. After harvest, if we're tilling in a lot of plant residue with some of these crops, you know, the nutrients go through this period of immobilization where we have a high carbon to nitrogen ratio. And so it ties up those nutrients for a period of time before the microbes can mineralize them. Okay. But in general, organic matter is a source of plant nutrients. Organic matter levels, we know, vary significantly for different regions. And even across the U.S., so this is a more general map from across the U.S., we get to the upper Midwest. You know, in general, we have a lot higher organic matter soils in this part of the country versus further south in the U.S. A couple of reasons for that. One is related to rainfall. Okay, in the southern part of the U.S., they typically have higher rainfall amounts, higher annual rainfall amounts compared to the upper Midwest. And then the other thing that's huge is temperature. Temperature affects microbial activity. Microbes, you know, they convert the organic matter, they mineralize the nutrients. And so one thing that's different here is in the southern part of the U.S., as far as cold temperatures, it's really, you know, only a couple of months in the year, probably December, January timeframe down in the southern part of the U.S. where the temperatures get pretty cold and slow down that microbial activity. Whereas in the upper Midwest, by the time we hit late October, clear through, you know, March timeframe, soils are pretty cold, and we've done a good job of slowing down that the soil microbes. And because of that, that actually helps us to preserve our soil organic matter. So that's another reason why we have higher organic matter in the upper Midwest. Okay, just a quick thing here as far as building organic matter. It's a lot easier to preserve our soil organic matter through different things like reduced tillage, you know, in different areas where we've got more slope in the fields. We've got terraced fields, grass waterways, things like that help to slow the erosion process. All those things help to preserve our soils and preserve soil organic matter. High crop yields as well. Adding that plant material back into the soil, that helps as well. But just to kind of work through this here, you know, if we wanted to raise our soil organic matter by 1%, it takes quite a bit of plant material to do that. So an assumption here. So an acre furrow slice of soil weighs roughly 2 million pounds per acre. And so what we're saying, to raise our organic matter by 1%, we want to take, we need roughly 20,000 pounds of plant material out there on that acre, okay? In order to do that, that's roughly 10 tons per acre. And we're going to need a lot more than just 10 tons per acre because of this factor down here. 75% of the crop residue that we add ends up getting oxidized or burned off as gas. And then there's only 25% that is added to that stable fraction of soil organic matter. So it really just drives home the point, it's a lot easier, it's a lot better to preserve our soil organic matter than to try to build it. And so using some of these conservation practices is a good idea. Okay, so we kind of already touched on this, probably don't need to spend a whole lot of time on this one here. Surface charges of the soil colloids or soil particles. Depending on the charge of our nutrients in the soil, they can either be held on that soil or they can be repelled by it. And the example that, a lot of times we deal with is nitrogen. So nitrogen has different forms in the soil. So we've got ammonium, NH4+, and then we've also got nitrate, which has that minus charge. So we'd mentioned before, the soil has these negative charges around the particle, these negative exchange sites. And so because ammonium is positively charged, it grabs on and holds to that ammonium, okay? Whereas with nitrate is now negatively charged, and the soil has that negative charge. The soil would actually repel the nitrate, and so it moves freely in that soil solution. So if we think about, we're getting into fall here, very quickly our soil temperatures hopefully will drop, and we're going to be starting with fall nitrogen applications. If we think about like an anhydrous application, that's a gas, but very quickly it goes and finds an extra hydrogen from water, and it converts to ammonium after we inject it into the soil. And so the soil is able to grab on and hold that for a period of time. And like we talked about before, with the cooler soil temps, that reduces our microbial activity, and we're able to preserve organic matter. And at the same time, we reduce the conversion from ammonium to nitrate when we're making those applications into colder soils. Okay. A couple other things here related to different nutrients in the soil. Tyler mentioned, so we will over the next few weeks go more in depth on each of these, well, not every one of them, but a lot of the different essential nutrients. Just the general categories here, if we were to separate them based on their charge. So the positively charged ones are cations. That would be like your potassium, ammonium, magnesium, and then you can see some of the others, calcium, manganese, zinc, and hydrogen. Those are all positively charged. Whereas the ones that are negatively charged in the soil, these are our nitrates, our sulfates, borate. A lot of times we think about, so our cations, they've got that positive charge. They're able to be held by the soil a lot easier. They're not, for the most part, they're not as mobile in the soil as some of these negatively charged anions, okay? Like nitrate, sulfate, boron, it's in the form of borate. All those are highly mobile in the soil. Okay, cation exchange capacity. We've already kind of talked a little bit about this. It deals with the charges, so, and the exchange sites on those soils. And this is dealing with the exchange, the soil with the soil solution, as well as the soil with the plant root, or the soil solution in the plant root. As more nutrients get taken up, more nutrients come off those exchange sites on the soil and go into solution and are available for plant uptake, okay? CEC acts as a buffer. Tyler's going to get into soil pH here in a minute, and the CEC, the higher CEC soils, basically create a buffer and make it so those soils they're a little bit more resistant to change. Okay, so for example, if we are dealing with a clay soil and we're trying to impact the soil pH, we're going to have to add a lot more lime to raise that pH compared to a sandy soil that doesn't have nearly as many exchange sites on it. Okay, but our soil CEC, so it helps us to manage our nutrients, but it can cause some problems like we talked about, you know, as far as impacting that soil pH for different soils. Okay, so organic matter and clays, they have different CEC values. We've talked through organic matter. There's a lot of exchange sites, a lot of those negative charges. The way they measure that is this milliequivalence. This is how CEC is measured. Milliequivalence per 100 grams of soil. That's how they had measured in the soil lab. But soil organic matter has a very high CEC. Some of these 2-to-1 clays have high CECs as well. But you can see by the time we get down to like our 1-to-1 type of clays, a lot lower CEC. Okay, just kind of a relative comparison there between them. There's different calculations we could do here. You know, if we were to know the exact amount of clays that we have out there in our soil organic matter, we could run through this equation and come up with, you know, what is our CEC, 17.5 milliequivalents per 100 grams. But we don't always know the exact clays. Most of the time we don't know the exact clays that we're dealing with out there. So we could use a general rule of thumb and say, you know, if we know our organic matter is 3%, we take 3 times 2, that gives us 6. And we know, you know, roughly we have 20% clay out in this field. If we're 20% clay, we take that times 0.5 to get 10, add those together to get 16. So ballpark estimate for CEC would be 16. Okay, so that's a little more simplified way to kind of work through it out in the field. So a couple slides back, it talked through different types of clays. One of them listed there was montmorillonite. That's a 2-to-1 clay. It has high shrink and swell. I just wanted to include this here because a lot of times, you know, we don't necessarily know, you know, what are the types of clays that we're dealing with. So that montmorillonite is a smectite. It's a type of smectite clay. Has high shrink and swell capability. And so you can see that a lot of the soils in western or northwestern Iowa have more shrink and swell ability than some of these other ones for the rest of the state that are illite. They're still a 2-to-1 type of clay, but they don't necessarily shrink and swell as much as the smectites. Okay. In general, you know, the more clay we have out there, the more organic matter, the higher the CEC. Whereas with our sands, we have lower CEC soils. Okay, the sands in general don't have exchange sites, but most of the time it's not going to be a straight up sand. You're going to have some small percentage of clay out there as well to provide those exchange sites. Okay, but just kind of a relative reference as we go from sands clear up to clay type of soils. If we put them side by side, a lot of times we'll say, you know, if we're dealing with a soil that's less than 10 CEC, you know, it's probably a higher sand content versus if we're anywhere from 50 clear up to 40 CEC, this is a higher clay content type of soil. And the properties are different because of that, because of the CEC and the number of exchange sites. Okay. So a higher sand content, it's going to require less lime to impact that soil pH. But we can't hold the nutrients as well, and so we have a higher leaching potential as well as a lower water holding capacity. Then on the flip side of that, with higher CEC soils, a greater ability to hold nutrients and supply nutrients, greater ability to hold water and supply water as well, but it's going to require more lime to impact pH because of that buffering capacity. Okay, last thing I'll mention here, then we'll flip over to soil pH. This general principle of, how are nutrients taken up? There's 3 different ways: root interception, mass flow, and diffusion. And a lot of that comes down to, what is the charge of that nutrient in the soil? Is it a cation? Is it an anion? Does it have that positive charge or negative charge? And the soil is going to hold it differently based on what the charge is. So a very small amount of nutrients are taken up by root interception. With that, the roots are growing, and they just happen to grow into an area that has that nutrient. Okay. So with zinc here, there is a decent amount of zinc that's taken up that way. Zinc, the plant needs a very small amount of zinc where it's a micronutrient. And so the plant can access a decent amount of its zinc need by root interception. Some of the nutrients that move freely in the soil solution, these are the anions, the ones that have the negative charge, like our nitrogen, our sulfur, our boron. You can see the high percentage that's taken up by mass flow because the soil can't hold that negative charge. And so those nutrients move freely with the water as it moves to the root. Okay. And then the last one over here on the right, this would be more like our nutrients that are held in the soil. Some of these, like, for example, potassium here, where it has that positive charge, it's held on the soil. And then as potassium is taken up by diffusion into those roots, it creates a zone around the root surface of lower concentration. And so basically the nutrients move from a high concentration to that lower concentration. So they're more is pulled off the soil into soil solution towards that root surface. So that's kind of the process of diffusion. Potassium is one that moves that way. This goes a little bit more in depth, the different pieces of how potassium moves, but in general, it's by diffusion, and that's what this is trying to show here. As more is taken up out of solution into the roots, more pulled off these exchange sites into that soil solution because of that concentration gradient. So one way that we kind of talked through this, I showed this at a couple different answer plot sessions this fall. Stealing this from first grade science class, talking about water and available nutrients, and it really does take both. And so we illustrated that with a cup of water and celery sticks. Okay, so with this here, the dye represents our nutrients, and so over on the left, we just have water. And if we just have water, we don't have any uptake of those nutrients. On the flip side of that, if we don't have any water, so for example, this year out in our fields, very low rainfall, very little water, but we still had, our nutrients were still out there in the soil. You'll see we did have a little bit of uptake. There is a little bit of a shading effect on this celery stick because it did take up the nutrients. But the best situation is over here on the right, where we have enough available water, enough available nutrients, so we see good uptake and movement of those nutrients into that crop to increase our yields. Okay, but with this, just illustrating, we need to have both adequate water and available nutrients. It's not necessarily representing just mass flow or diffusion. Those are more related to the charge of the nutrients. But it does illustrate the point that we need both water and available nutrients for good uptake. So I think from here on to soil pH. Tyler, are you there?
Yes, I am. All right, so soil pH, guys, it is a measure of the hydrogen ion concentrations within the soil. The more hydrogen that you have in the soil, the more or the higher your pH is. Okay. Now, the thing that we have to remember is that pH is on a logarithmic scale. What that means is that every time we go down one level, we're actually getting 10 times as much hydrogen ion concentration. So, for example, if I go from 7 down to a pH of 6, I actually have 10 times as much hydrogen ions at a pH of 6 as compared to a pH of 5. If I go from 7 down to 5, for example, now I'm actually got 100 times. Okay. So a change of pH from 6 down to 5.8 actually doubles the amount of hydrogen ions in that soil solution. Okay, now pH is really important because it affects all of the other nutrient availabilities, especially something like a phosphorus. Phosphorus is one of the most affected nutrients when it comes to pH. And it's because it forms a bond with things like calcium, aluminum, and iron, depending on the pH. Okay, now this bond isn't necessarily a bad thing because if phosphorus or phosphate did not form that bond, phosphorus would actually leach much like nitrogen does because phosphorus is negatively charged. So the bond isn't necessarily bad. The key thing is, though, we have to have the right pH balance in order to make sure that we're getting that phosphorus available. Now, each of our crops does have a different pH range in which it should be planted. Alfalfa is one of the most sensitive crops we plant in Iowa to pH. It really likes it more around that 7, 6.8 to 7 is going to be ideal for alfalfa. When you look at soybeans, we can go from 6 to 7.2. Corn is actually more tolerant. It can go from 5.5 to 7.5. Okay, so that's ideal. You can see some of the other ones here. Blueberries, for example, if you want to raise blueberries, you better drive that pH down very low. Now, with pH, the reason why we have to continually monitor our pH is because of the things that we're adding to the soil. So, for example, here's all the different nitrogen forms and actually sulfur forms that do decrease pH. Now, the reason why it decreases pH is, remember, as we're decreasing pH, we're increasing the hydrogen ion concentration. So if you think about it, we apply most of our nitrogen in, let's say, well, let's just take anhydrous ammonia, for example. It's NH3. Okay, so NH3 over time converts to nitrate. So first it goes to ammonium. NH3 goes to NH4 because it grabs a hydrogen ion off of water. So immediately we actually do take a hydrogen from the system, and we do see a slight increase in pH when we apply anhydrous ammonia. The problem is that over time, the anhydrous ammonia will convert over to nitrate, or that ammonium, that NH4 will convert over to nitrate, NO3. You'll notice that we lose the hydrogens, and that hydrogen, when we lose those hydrogens, ends up contributing to lowering the overall soil pH. So each one of our nitrogen forms does lower pH. And actually, if you look at pounds of calcium carbonate for 100 pounds of nitrogen, it's actually about the same for every single form of nitrogen fertilizer that we put out there. So there's really not a lot of difference. All nitrogen fertilizers, regardless of their source, do contribute to lowering pH. And this includes manure as well. Okay. And then sulfur will also lower pH as well. Okay. Whether it's in the sulfate form or elemental sulfur as well. A lot of you guys know that elemental sulfur will lower the pH. Some people will try to use elemental sulfur, actually lower pH. Okay. Now, when we're talking about pH, the soil pH is a representation of the hydrogen ion concentration in the water solution. However, if we only consider how much hydrogen is out in the solution, it would take about a third of a pound to neutralize all the hydrogen ions in that soil for 1 acre. And I don't know about you guys, but I don't think I could effectively spread a third of a pound evenly across an acre. Okay, but the problem that we have is that it's not just the hydrogen ion concentrations in the water we have to deal with, We also have to deal with the hydrogen ion concentration on the CEC, on the exchange site. Because hydrogen is a positively charged ion, it will connect into that soil. And the amount of hydrogen in the soil solution is a direct reflection of the amount of hydrogen ions on the colloid. Okay. Now, we refer to the hydrogen ion concentration on the exchange sites as reserve acidity, the hydrogen ions concentration in the water as active acidity. Okay, so the reserve acidity basically is the hydrogen ion concentrations measured as a buffer. Okay, now a lot of you guys are familiar with pH and liming. We usually go off of the buffer pH in order to make our lime recommendations. The reason why is because each soil is a little bit different. The more CEC that you have, or the higher your CEC, the more lime is going to be required to change your soil pH. So to give you a little demonstration of this, we'll start this video here. All right. So I have two different jars of water here. Okay. We have a low CEC soil, which is represented by this jar, and we have a high CEC soil over here. Okay, now what this is representing, the water is representing the total amount of positive charges in the soil. In other words, this is representing the lower CEC with the smaller amount of water and the high CEC soil over here. Now, if I start my pH calibrator here and I look at the water, we'll just let it go down. So we're at about 8.3 pH right now starting. And we're at 8.3 with this one. So they're the identical pH with both of these. Now, I have 2 shot glasses full of vinegar here. I'm going to add them to each one of these. I'm going to mix them up. Which one of these would you guys assume would now have the lower pH? Well, let's check it. So over on the right, with the lower CEC, we have a pH of now 3.7. Over on this side, we have a pH of 5. Okay, so it was the exact same amount of acidity that we added into these 2 jars. However, they were different pHs because of the fact that we have much smaller amount of exchange sites, a much smaller amount to change over here. So it's the same thing that happens in our soils, where these lower CEC soils are much easier to change. A sandier soil or lighter soil will not require as much lime as what our very heavier soils tend to require, because you have a lot more of a buffering capacity with these type of soils than we do with others. So it's kind of a neat demonstration to show you how that reverse or reserve acidity works. All right, so how lime works in the soil, what it's doing, and this, it's really important, it's got to be some sort of a calcium carbonate or magnesium carbonate. Basically, the calcium is exchanging on the soil particle here and is pushing the hydrogen off. And when it does that, the carbonate comes apart and the 2 hydrogen ions connect onto the oxygen, and we're left with H2O and CO2. So that'd be calcium carbonate. Now, some people assume that calcium sulfate will do the same thing. Calcium sulfate does not act as a liming agent. You have to have either calcium carbonate or a magnesium carbonate, a lime source there. Now, as far as the neutralizing value of lime, a lot of it's going to depend on the particle size, the purity, and the effective calcium carbonate equivalency. So the neutralizing value we refer to as the calcium carbonate equivalency. Basically, this is how much calcium carbonate is actually in the solution or in the product. So pure calcium carbonate would have 100% CCC or ECC or CCE. You'll often see this as calcitic lime. This is what a majority of our stuff is. Either it's calcitic lime or dolomitic lime. Either one will have a fairly high efficacy, although I've seen it as low as 50% and as high as 100%. Okay. Now, some farmers get caught up in like the calcium to magnesium ratio in the soil, guys. Overall, I don't really care. There's not a lot of difference, and it's been shown that the calcium to magnesium ratio really doesn't affect crop growth much. But calcitic lime just has calcium carbonate. Dolomitic lime has both calcium carbonate and magnesium carbonate as well. So you get a little magnesium in there. Okay, so that's what you're measuring with the effective calcium carbonate equivalency. Okay, now another thing we got to look at is the effectiveness of the lime over time. Okay, the finer that it's ground, the quicker that it acts. And to demonstrate that, we will do one more demonstration here. Okay, so right
this
now,
looks kind of dangerous.
What's up?
I said this looks kind of dangerous here, Tyler.
I know. All right, I got Pepsi here, which is very acidic, right? Also delicious. Okay, so got Tums. So this is Tums are basically calcium carbonate. Throw that in there. Mix it up. Not a lot happens. Getting a little fizzing, not a lot happens, right? Okay. Go on to the next one. Now we have a little bit more of a finely ground lime, a little bit. It's still pretty big here. So let's see what this does. Getting a lot more fizzing, but still not a lot there. Okay, now I have a very fine ground lime here. So this is very fine ground. Took me a lot of work to get that all ground up here. So when I put that in, mix it up. Now you can see we get foam throughout the whole thing because basically it immediately acts with that sodium or with that soda in there. Whereas you can see this one's still got a bunch of pieces left on the bottom there, and this one is still whole, okay? And so with that, what's demonstrating is basically that the finer ground lime, the more quickly that's going to react with the soil. Okay, now there's a couple different versions or a couple different methods you can get for lime. Hold on, hopefully it's, yeah. Is it sharing there, Darren? Yeah, I think it is.
Yep, you're good.
Okay. So you can get egg lime, and egg lime's the most common, whether it be calcitic or dolomitic lime. And by the way, guys, dolomitic, some people get so bent out of shape over dolomitic and they'd rather have calcitic lime. Really, dolomitic lime, all it's saying is that you have greater than 5% magnesium. So it's not a huge bunch of magnesium in there anyway. But basically with this, it's a combination of all the different sizes of lime. That's why we make a normal recommendation for lime as being a 4-year rec. Pell lime is lime that's been very, very finely ground, and therefore all of it passes through a 100 mesh screen, very quick to react, but you don't get a lot of activity out of it. It usually only lasts about 3 to 4 months at most. Okay, so where I would use Pell Lime is if you got a guy that's renting ground that just needs to raise the pH for 1 year and is done. Or if you made a mistake, you planted your alfalfa before you got the lime on and didn't correct the soil pH, this is a good way as well to correct that as well. Otherwise, I would prefer ag lime, mainly because you get a little bit longer activity out of it. It tends to last a little bit longer as well. As far as liming recommendations, it depends on your soil depth. With more and more people going to no-till, this is one thing that we do have to consider. If you're going a very shallow tillage or no tillage at all, we actually have different liming recs than if we were going our more normal tillage depths. Okay, so, and a lot of us have programs that do this for us, but just so you're aware, this is where that data comes from. And if you don't know which rec you're using, whether it be no-till or conventional till, you should at least check to make sure that you're using the right recommendation. All of it, though, is based off buffer pH, because again, like we demonstrated, that buffer pH measures the hydrogen ion concentration on the exchange site, and therefore gives us a much better idea of how much lime is going to be required to take over and actually change that pH. Okay, final things, guys, and I'm going to zoom through this. High pH soils, unfortunately, there's not a lot we can do. Okay, this is looking at the amount of pH or amount of elemental sulfur that would be required to lower your overall pH. Basically, guys, we're looking at tons per acre. And then, by the way, these calcitic soils that got really high pH, generally, they have 5 to 10% free calcium carbonate. And for every 1%, we would need an additional 3.25 tons of elemental sulfur to neutralize that free calcium carbonate. So it's really not an option to lower the pH in high pH soils, but we can raise pH in low pH soils.